Van't Hoff vector. I will teach you the basic and advanced concepts of Van't Hoff vector and JEE Main numerical problems. Now we know that colligative properties depends on number of solute particles. Colligative properties do not depend on nature of solute. Hence remember this important point. Here, let me teach you one of my favorite questions. Why we need to study Van't Hoff vector? Well, consider 100 ml of water in this jug and 100 ml of water in this jug. Now I put 1 mole of sodium chloride in 100 ml of water. I also put 1 mole of sugar in 100 ml of water. We can observe that 1 mole of salt solution has more boiling point than 1 mole of sugar solution. Now let me ask you, why 1 mole of salt solution has more boiling point than 1 mole of sugar solution? Well, these both solutions have equal number of particles. But colligative properties cannot explain this difference of elevation of boiling point between these two solutions. So it is Van't Hoff vector which explains this difference in elevation of boiling point. Thus we need to study Van't Hoff vector to explain this difference in elevation of boiling point. Remember that colligative properties only explain any change or elevation when a solute is non-electrolyte, like sugar, urea, etc. While we need to study Van't Hoff vector when a solution is an electrolyte, like sodium chloride, magnesium chloride, etc. Now we will learn two important concepts to master Van't Hoff vector: degree of dissociation and degree of association. We define degree of dissociation as out of 1 mole how much solute dissociates into ions. Remember that we denote degree of dissociation by alpha. For example, consider this reaction. We know that in this equation, 1 mole of sodium chloride 100% dissociates to 1 mole of sodium ions and 1 mole of chlorine ions. I write degree of dissociation of sodium chloride alpha is equal to 1 plus 1 is equal to 2 moles. It means that the degree of dissociation of 1 mole of salt is 2 mole. Let me repeat it. It means that the degree of dissociation of 1 mole of salt is 2 mole. Hence note down this important concept. On the other hand, we define degree of association as out of 1 mole how much solute combines into ions or molecules. Remember that degree of association is also denoted by alpha. For example, consider this reaction. We can see that 2 moles of acetic acid 100% associate to form 1 mole of dimer acetic acid in the presence of benzene. I write degree of association of acetic acid alpha is equal to 1 mole. It means that 2 moles of acetic acid are 2 molecules of acetic acid combined together to form 1 molecule. Let me repeat it. It means that 2 moles of acetic acid are 2 molecules of acetic acid combined together to form 1 molecule. Hence note down this important concept of association. Now what is Van't Hoff vector? Well, it is super easy. Let's consider this reaction. 1 mole of sodium chloride 100% dissociates to 1 mole of sodium ions and 1 mole of chlorine ions and water. Now listen carefully. Initial number of moles of solute before dissociation is 1 mole. I mean, there is only 1 mole of salt or sodium chloride. On the other hand, final number of moles of solute after dissociation is 2 moles. I mean 1 mole of sodium ions and 1 mole of chlorine ions. Here, Van't Hoff factor is equal to final moles of a solute after dissociation upon initial moles of a solute before dissociation. Personally, I teach Van't Hoff factor as I is equal to final moles upon initial moles. Now in case of this reaction, I write Van't Hoff factor I is equal to final moles upon initial moles. Final moles is equal to 2 moles upon initial moles is equal to 1 mole. I get I is equal to 2. Thus the Van't Hoff factor of this reaction is 2. Therefore we define Van't Hoff factor as the ratio of final moles of a solute after dissociation to the initial moles of a solute before dissociation is called Van't Hoff factor. We know that we denote Van't Hoff factor by I. Thus remember that Van't Hoff factor is the ratio of final moles of a solute to initial moles of a solute. Now we will learn calculating Van't Hoff factor. We already know that Van't Hoff factor I is equal to final moles of a solute upon initial moles of a solute. Firstly, we will learn calculating Van't Hoff factor of dissociation reactions. Now consider this reaction and find its Van't Hoff factor. Well, we know that initial moles of a solute calcium chloride is 1 mole, while the final moles of a solute is 1 mole of calcium ions plus 2 moles of chlorine ions is equal to 3 moles. We know that I is equal to final moles of a solute upon initial moles of a solute. The final moles of a solute is 3 moles upon the initial moles of a solute is 1 mole. I get I is equal to 3 moles. Thus Van't Hoff factor of this reaction is 3. Secondly, consider this reaction and find its Van't Hoff factor. Well, we can see that the initial moles of a solute is 1 mole. The final moles of a solute is 2 moles of potassium ions and 1 mole of sulfate ions is equal to 3 moles. We know that Van't Hoff factor I is equal to final moles of a solute upon initial moles of a solute. The final moles of a solute is 3 moles and the initial moles of a solute is 1 mole. After calculation, I get 3. Hence the Van't Hoff factor of this reaction is 3. Here remember this very important point. Van't Hoff factor of dissociation reaction I is always greater than 1. Let me repeat it. Van't Hoff factor of dissociation reaction I is always greater than 1. Hence note down this important concept. Now we will learn calculating Van't Hoff factor of association reaction. Let's consider this important reaction and find its Van't Hoff factor. Well, we can see that initial moles of a solute before association is 2 moles, while final moles of a solute after dissociation is 1 mole. We know that Van't Hoff factor I is equal to final moles of a solute upon initial moles of a solute. The final moles of a solute is 1 mole, the initial moles of a solute is 2 moles. I get I is equal to 1 by 2. Thus the Van't Hoff factor of this reaction is 1 by 2. Remember that Van't Hoff factor of association reaction I is always smaller than 1. Let me repeat it. Van't Hoff factor of association reaction I is always smaller than 1. Hence note down these basic concepts of Van't Hoff factor. Now I will teach you some advanced concepts of Van't Hoff factor for competitive exam. Firstly, we will learn one important relationship. I mean relationship between Van't Hoff factor and degree of dissociation or association. I will teach you super easy method to form this relationship for any reaction. Now let's consider this reaction. Firstly, I write initial moles of a solute and final moles of a solute. We know that the initial moles of sodium chloride is 1 mole because it is not yet dissociated into its ions. So the initial moles of sodium and chlorine ions is 0 and 0. To understand final moles of a solution, consider this simple analogy. Let I have $10. I spent $2. How many dollars are remaining? I say 10 minus $2. Secondly, if I have $10, I spent X dollars. Then I say the remaining dollars are 10 minus X dollars. Hence remember this example. Now after some time, this sodium chloride slowly dissociates to sodium and chlorine ions. Let it is alpha moles of sodium and alpha moles of chlorine. I say I have 1 mole. I spent alpha mole. So how many moles is remaining? The answer is 1 minus alpha mole, like 10 minus X dollar. Thus the initial moles of a solute is 1 mole and the final moles of a solution is 1 minus alpha, this alpha and this alpha moles. Now what about its Van't Hoff vector? Well, we know that I is equal to final moles of a solute upon initial moles of a solute. The final moles of a solute is 1 minus alpha plus alpha plus alpha upon the initial moles of a solute is 1 plus 0 plus 0. After calculation, I get 1 plus alpha. Thus the Van't Hoff vector of this reaction is 1 plus alpha. Using this equation, we can find the Van't Hoff vector of this reaction at any moment. For example, let this sodium chloride 100% dissociates to sodium and chlorine ions. Then the degree of dissociation alpha is equal to 1. I put the value of alpha in this reaction. I get 1 plus 1 is equal to 2. Thus the Van't vector of this reaction is 2 if sodium chloride 100% dissociates into ions. Hence noted down this important relationship. Now consider this association reaction and find relationship between I and alpha. Here my students did a blunder. For example, they write initial moles of a solute is 2 moles and that of ions is 0. It is totally wrong. Remember that we always take initial moles of a solute as 1 mole. Let me repeat it. We always take initial moles of a solute as 1 mole. Now to avoid this mistake, I teach this easy trick. Here, the stoichiometric coefficient of acetic acid is 2. Now divide both sides by 2. I mean by this stoichiometric coefficient. Now you can easily avoid this mistake. I mean 1 mole of acetic acid associates to 1 by 2 ions or molecules. Thus I write initial moles of a solute is 1 mole and 0 mole. After some time, pi by 2 moles of ions or molecules associate together because 1 mole of acetic acid associate to 1 by 2 mole. Now how many moles of acetic acid is remaining? It is still 1 minus alpha moles. We know that Van't Hoff vector I is equal to final moles of a solute upon initial moles of a solute. The final moles of a solute is 1 minus alpha plus alpha by 2 upon the initial moles of a solute is 1. After calculation, I get 2 minus alpha upon 2. Thus the Van't Hoff vector of this association reaction is 2 minus alpha upon 2. Using this equation, we can easily calculate the Van't Hoff vector of this reaction at any moment. Hence noted down this important concept. Now we will learn important formulae of colligative properties. We know that colligative properties depend on number of solute particles. When particles of a solute increases or decreases in a solution, colligative property increases or decreases. Firstly, we will learn colligative properties when a solute is non-electrolyte like urea, sugar, etc. Now we use these formulas of colligative properties. On the other hand, we will learn colligative properties when a solute is an electrolyte like sodium chloride, magnesium chloride, etc. We know that in case of electrolyte solution, the particles of a solute change by Van't Hoff factor I. So the colligative properties also change by Van't Hoff factor I. Let me repeat it. The particles of a solution change by Van't Hoff factor I. So the colligative properties also change by Van't Hoff factor I. Thus all these colligative properties change by Van't Hoff factor I. I mean, I multiply all these formulae by Van't Hoff factor I. Thus remember these two types of colligative properties in case of non-electrolyte solution and electrolyte solution. Now I will teach you two important JEE Main numerical problems using this simple method. Consider this JEE Main problem. Mercuric potassium iodide is 40% ionized in aqueous solution. The value of its Van't Hoff factor I is dash. Well, we already learned the relationship between I and alpha. We know that 1 mole of mercuric potassium iodide ionizes into 2 moles of potassium ions plus 1 mole of HgI4 ions. Now the initial moles of a solution is 1 mole, 0 mole and 0 mole. The final moles of a solution is, we know that 1 mole of mercuric potassium iodide ionizes to 2 moles of potassium ions. I write 2 alpha. And to 1 mole of HgI4 ions, I write alpha. Now how many moles of mercuric potassium iodide is remaining? It is 1 minus alpha. Now Van't Hoff factor I is equal to final moles of a solute upon initial moles of a solute. I is equal to the final moles of a solute is 1 minus alpha plus 2 alpha plus alpha upon initial moles of a solute, which is 1. Thus minus alpha and this plus alpha cancel out. I get I is equal to 1 plus 2 alpha. Using this equation, we can find the Van't Hoff factor of this reaction at any moment. We know that when a reaction 100% dissociates, alpha is equal to 1. Similarly, if a reaction 40% dissociates, then alpha is equal to 0.4. Now I will put the value of alpha in this equation. I write I is equal to 1 plus 2 into 0.4. After calculation, I get I is equal to 1.8. Thus the correct option is B. Hence using this simple method, we can crack these questions. Finally, let's consider this another JEE Main question. When 20 gram of naphthoic acid is dissolved in 50 gram of benzene, a freezing point depression of 2K is observed. The Van't Hoff factor is dash. Firstly, I write the given data. The given mass of naphthoic acid is 20 gram. Remember that it is solute and its molar mass is 172 gram. Secondly, the given mass of benzene is 50 gram. Remember that benzene is a solvent. The value of Kf is equal to 1.72 kg Kelvin per mole. The freezing point depression is 2 Kelvin. We are asked to find Van't Hoff factor I, which is unknown. Now we know that depression in freezing point is del Tb is equal to Kf into m into I. Here this m stands for molality. Now to find molality, we need the number of moles of a solute. So in the first step, I find the number of moles of a solute. The solute is naphthoic acid. I write number of moles of naphthoic acid is equal to given mass upon molar mass. The given mass of naphthoic acid is 20 gram and its molar mass is 172 gram. After calculation, I get 0.116 mole. So the number of moles of naphthoic acid is 0.116. In the second step, I find molality. We know that molality M is equal to moles of a solute upon mass in kg of a solvent. The number of moles of a solute is 0.116 mole. I write 0.116 mole. The mass of benzene, which is a solvent, is 50 gram. I convert it to kg. In kg, it is equal to 0.05 kg. I write here 0.05 kg. After calculation, I get 2.32 mole per kg. Thus the value of M, which is molarity, is equal to 2.32 kg. In the third step, I find Van't Hoff factor I. I rearrange this equation. I get I is equal to del TB upon Kf into M. Now I put all these values in this equation. The value of del TB is 2K, the value of Kf is 1.72 and the value of M is 2.32. After calculation, I get I is equal to 0.5. Thus the Van't Hoff factor of this reaction is 0.5. Hence the correct option is A. Therefore, using this method, we can crack any numerical problem.